Hi everyone, I'm Thomas Wall from HuggingFace, and today we're going to talk about an exciting topic, the future of NLP. Well, more precisely, the future of transfer learning in NLP. To be honest, this talk is like a personal walk through some of my favorite paper and research direction of the last few months, so I really hope you enjoy it as much as I do. We're going to talk about a lot of things. We start by talking about model size and the data requirements. Then we'll talk about in-domain versus out-of-domain generalization. We move on to fine-tuning, model evaluation, what are the problems, what are the limits of these things. And then we end up discussing common sense and inductive biases, okay? So let's start by the elephant in the room, okay? You probably have noticed the models are getting bigger and bigger. There is a nice graph that Victor San made last year, which shows how these models are just getting crazy bigger. It's exponentially increasing. So now the state-of-the-art models, they are over 1 billion parameters, and they're actually far above that because several models are now like 10 billion parameters, like T5 and the Turing model from Microsoft. And you have a huge problem with these models because they don't even fit on one GPU and not even on two GPU. You need like 4 to 8 GPU just to load this model and to run them with a batch size of 1. Okay? Now, why is it a problem? Well, that's a huge problem because if you check like the current leaderboards, for instance, the Glue leaderboard that you can see here, you can see that the competition is narrowing, okay? It's all about the same teams now. There's like Google, Microsoft, Amazon, Baidu, Facebook, and that's pretty much it. You see there's no academics there, okay? Because just the models are too big, the computational requirements are too big. So there's a huge problem of diversity and also where does academia fits in current research in NLP, okay? Another problem that you've probably seen is the environmental cost of training this model, okay? They require a lot of energy consume and generate carbon dioxide, and so we know that training this model is not good for the environment. What can we do? And the last problem was very well stated by François Chollet. It means that if we just go bigger, what do we expect? Do we expect like to see a phase transition at some point? Or is it just like building bigger scales to try to reach the moon? Okay. Now there is another option, which is to go the other way. We know that since this very nice paper of Yann Lequin, I really like the title, Optimal Brain Damage, in 1989, we know that neural nets are overparameterized. They have too much weights. We can just prune them, and the most recent example is the lottery ticket hypothesis, which says that if you take a randomly initialized model, you can actually find a subset inside of these models which already has good performances on your test task. Okay, you don't even need to train your model. You can just take this big model and find a subset, the small subnetwork inside of it that's already nice for your task. And we see that in fine-tuned model as well. When you fine-tune model, you can remove the weights, you can select the weights, and you keep the performances. So here you see this example on NLP task, where actually you can remove like 90% of the weights and keep the same performances. Okay, so we want to push in this direction. So here is a small promotion. We're doing a competition that started actually 2 days ago, which is about getting the more efficient models that you can. Okay, it's called Sustain LP. It's a workshop that we collocated with EMNLP at the end of the year. And the goal is to get this to the same threshold as the current state-of-the-art model, like BERT-based, for instance, and just to try to be the most efficient, the most energy efficient that you can, okay? The competition is only on inference for now, because inference is actually one of the biggest part when you look at the lifetime contribution of a model, like the lifetime computational cost, when these models, they are like deployed in application on like thousands of servers, actually inference cost is the biggest part of their lifetime environment cost, okay? So if we can get better on inference, we're like already a long way through our goal of getting more efficient models. Now, how can you reduce the size of the models, okay? So we start by this. Let's go a bit into depth. There are mostly like 3 techniques that you can use. The first one is called distillation, second one is pruning, and then there is quantization, okay? So distillation, here is a good example. We made a model called DistillBERT at the end of last year, which gets like 91st performances of a BERT model on Glue, and is like 40% smaller. How you do that? Well, you take BERT as a teacher model, which means you have a pre-trained BERT, and then you will train a student model, which will be smaller. And you train the student model to reproduce the generalization capabilities of the teacher, okay? So here is a good example. You see this sentence? I think this is the beginning of a beautiful, and then the model is asked to complete. So BERT is trained like that. BERT is trained to predict mask token. So here you see the top prediction of BERT, and you see they all make sense, okay? You see day, life, future, story. All these top prediction that BERT thinks are possible, they all make sense. This is what we call generalization. The BERT model learn to generalize, okay? Beyond just a simple training example in this sentence. And what we'll do is that the student's model will be trained to generalize in the same way as the teacher model. So it will learn the inductive bias that the teacher model has learned. It's very easy. We just do a cross entropy. It's called the knowledge distillation. And we just do a cross entropy between the output of our students and the output of our teacher, okay, when we train. You can use temperature to like emphasize the lower probability. That's a very common trick in NLP. So now a lot of people have been publishing on distillation at the end of last year. You can see a couple of papers, like the state-of-the-art distillation models are kind of very complex now. TinyBERT is a good example, where the student model actually has a smaller size of hidden states, and they try to make the student model also mimic the hidden states of the teacher. So you have down projection from the teacher to the student. They also use a lot of data augmentation, so it's kind of tricky to know exactly what is what part of the good performance of this latest model come from data augmentation, or what part come from distillation. But definitely, people can get like very small models with good performances using mix of distillation and data augmentation. Now let's move on to the second technique you can use to reduce the size of the model, okay, which is called pruning. In pruning, you directly work on your teacher model and you actually remove weights from this model to make it smaller. Okay? There are various ways you can prune, and one simple way is actually to remove attention heads in your transformer. It was shown by two nice papers of last year, one by Elena Wojta from Edinburgh University and the other by Paul Michel at CMU, and they show that you can actually remove a lot of the heads of transformer model after they've been trained, and you can keep very good performances. So on the top, you see the results on translation. You see that you can actually remove 90% of the heads and keep a very good blue score. And on the bottom, you see the result on GLUE, which is the general language understanding benchmark, and you see pretty much the same performance. So one way you can identify the heads you should remove is by using what Paul Michel showed, called the score, the head importance score, which is actually the gradient of the loss with regard to the output of the attention layer. And if you remove the less important heads first, you can actually keep this very good performance. What is interesting is that you see on this last graph here is that you can actually, if you remove some heads that are less important for one task, here it's on MNLI, you can actually see that this is quite resilient to domain adaptation. So here in MNLI, you have two parts from the dataset. You have what is called the matched dataset and the mismatched dataset. And if you remove some heads that are not useful for one, you can see that actually it's kind of related. Well, okay, the graph is not exactly linear, but there is some correlation with heads that are not important on another domain, okay? So which means that there are some heads that are actually not useful for anything, at least on MNLI, okay? That's interesting because it means this is quite resilient to domain adaptation. Now, you can also directly remove the weights. When you remove the weights, it's actually more fine-grained because each specific weight can be removed, but the problem is that you will end up with very sparse matrices that are not so good for GPUs. We'll talk about that later. But you can get also very good performances. Here is a nice paper from the ASAP team with Jerry Walwend and Ziheng Wang, and they did a very nice paper. They did very nice work on pre-trained models as well, removing weights with a nice differentiable L0 pruning. Okay, they use like a hard concrete distribution, which is basically the Gumbel of Max Trick. Okay, and the last part is actually layer pruning. In layer pruning, this is a nice paper by Angela Fan of last year at Facebook as well. They actually remove full layers of the transformer. So this is really a lot. Okay, you remove this full layer. So the way you can actually do that and have the model still behave quite well is by training the model to be resilient to that. So during pre-training, you will randomly remove layers, like a dropout. Okay, it's a structured dropout. You drop layers, and so the model learns to actually behave well without some weights. It works well because these transformers layer, they are like a repetition of the same module, okay? And you have this residual connection, this shortcut connection, which means that actually one layer and the next one, they are always connected with a shortcut as well. So when you remove a layer, it's actually less aggressive than in some like fully connected models without shortcut connection. So layer pruning is very interesting as well, and you keep these dense matrices because you remove full blocks of weight. So why am I talking about this problem of sparsity? Well, because all these models, we run them on GPUs. And GPUs are, or TPUs, but GPUs and GPUs, they are really optimized for dense matrix multiplication. Okay, they have troubles with sparsity. And when you use this sparse model on GPU or TPU, they are usually way slower. They can be like 3 to 4 times slower to run. So they're smaller, indeed, but they're also a lot slower. And it's also not efficient. So you're losing what you were actually looking for, which was energy efficiency. So there are various ways you can try to circumvent this. One way is to use what OpenAI was promoting, which is block sparsity. So instead of removing all these weights, single weights, you actually remove blocks of weights. And these blocks have the nice size that is adapted to your GPU or TPU kernel, which means that you keep dense matrix multiplication. Well, you can remove blocks, but actually when you do like strong sparsity, it means you just keep blocks actually, okay? Your matrix is just a few blocks, as you can see here. So this helps you. Another approach is actually to make a full sparsity, but with patterns that you actually control, so you can keep advantages of optimized CUDA kernel. Now, the more you structure your sparsity, usually the less performances you can get because you're actually constraining the model, okay? So if you have like unstructured sparsity, you usually can keep the best performances on the metrics, but you lose the efficiency. And the more you structure the sparsity, the better your energy efficiency is, and usually the worse your performance is. So another alternative is to actually switch chips and try, for instance, the new IPU from GraphCore, which are chips that are specifically designed for sparse models. Okay, they are made of a lot of small modules that can process data independently and have this small RAM associated to them, and they can actually process sparse matrices very efficiently. Now, the last technique I want to talk about when we're talking about shrinking model is quantization. Quantization is also very interesting. We know that using float 32, using full precision float weights is actually not the most optimal way. We know that these neural networks, they also work well with half precision and even quantized integer. So we can do that from our transformers as well, okay? We will convert the float to the full precision weights into integer 8, so we really reduce a lot the size of our model. And we use dynamic quantization, for instance, where you have a scaling and 0 point conversion. And this works very well. There was a nice work by Intel called Q8BERT, and it's really working well. You can try it. It's very easy in PyTorch and TensorFlow as well. It's very easy to apply quantization. And a bit like layer pruning, you can do training-aware quantization. So you kind of tell your model is going to be quantized at the end, okay? You actually train it in a way that it's getting used to be quantized. And so you have better performances as well at the end, okay? Okay, we've talked a lot about these big models, how to reduce the size. Now there is another thing that is increasing exponentially recently in NLP, which is the requirement for more data. People are using more data for pre-training, and people are also using more data for fine-tuning, okay? So there's a problem because when you compare two models that were pre-trained on two different data sets of very different size, it's really hard to tell if one model is better because it was pre-trained on more data, or if it's better because usually of the like novel architectural design that people introduces. A good recent example of last year was ExcelNet, the transformer from Google. That was the successor of Transformer XL. And XLNet use a smart autoregressive training. So you could actually do autoregressive training while having the possibility to attend to both contexts, to left and the right context. Usually when we do autoregressive training, we only go one way, so our model is masked. The right context of each token for the model is masked. But in XLNet, actually, they do autoregressive with a random permutation. So the model actually learns to pay attention to both contexts. Now the problem was that XLNet was also trained on a lot more data than BERT. So when they compared to BERT, it was really hard to tell what was the difference, what was the improvement that came from training on 20 times more data, and which improvements came from having this new autoregressive architecture. So there was a huge debate, and actually it was kind of settled by Roberta, which was a very simple BERT architecture, just exactly the same as BERT, but just trained on more data, basically. And Roberta outperformed XLNet, which showed that basically there was the bitter lesson of NLP and the bitter lesson of machine learning in general, as Richard Sutton talk about it, which is that if you have more data, it's usually outperform having a smarter model. Okay. And now there is this recent paper that we're going to talk a lot more about, which is called Scaling Laws for a Neural Language Model. This is a paper from OpenAI, and it's a really in-depth study of what happened when you increase the data size and when you increase the model size without changing the architecture. So it's a very good study. Now this is for pre-training, but we see the same on fine-tuning, which is that people, when they fine-tune, they do a lot of data augmentation. And a good example is the Winograd Schema Challenge. The Winograd Schema Challenge was a very interesting dataset for a long time. It's very simple. You see one example here. You have a sentence that say, for instance, the trophy would not fit in the brown suitcase because it was too big. And the question is, what was too big? Was it the trophy or was it the suitcase? And the model has to do a classification between these two ones, okay? So that's very interesting because you need some common sense. You need to know that suitcase is usually bigger than a trophy. And the way it was solved, and for a long time it was a very hard challenge. It's a very small one, you only have like 300 examples. And for a long time it was very hard to get good performances for deep learning models on that. And the way it was solved was actually to generate artificial data augmentation datasets with some heuristics, extracting from Wikipedia sentences where you have 2 times the same noun, like 2 times trophy, and replacing one of them by it. Like this, you can build with these heuristics, you can build a huge dataset from any crawl text dataset. And you can pre-train your model on that, and then do this fine-tuning on the Winograd Schema Challenge after that. And you can solve the task. But you can see that it's not very, we're not really happy about that, because scientifically we have not really learned anything about common sense by doing that, okay? We've just learned that more data is better. So let's talk a bit more about pre-training first, okay? So I talk about the Scaling Laws paper. Let's go into depth in this paper. So this paper is about one single architecture. It's about the transformer trained for autoregressive language modeling, okay? So you only have the left context for each token. These are transformers that are trained to predict the next token given the beginning of a sentence. This is GPT-2, but they experiment with many sizes of the datasets, and also they did some nice scan on the architecture. There was always some question about transformer, which is what is the optimal ratio of the number of heads with regard to the model size? What are the optimal ratio of the number of layers with regard to the dimension of the models? And I kind of show that all this doesn't really matter. As long as you're in a very flat sweet point where you have this nice hyperparameter that was pretty much the original attention is own unit parameter. As long as you're in this sweet spot, you're good. So these models are very actually robust to this simple hyperparameter exploration. And what they show is that just by scaling model size and scaling the dataset size, you have a very clear power law, which means that it's actually exponential. Actually, that's what it means. It's exponentially decreasing. So if you double your model size, you have this linear improvement in performances. If you double your dataset size, you also have this linear improvement. But this power law, they go over very wide ranges. They go over orders. They went on over orders of magnitude. Now you can read this paper, it's very interesting. They show that two interesting things for me. One was that there was a follow-up paper by Eric Wallace at UC Berkeley, which showed that it's actually better to have a too big model. It's actually better that your model is more big than we used to think. And for the dataset. So if your model is actually slightly too big for your dataset, in the way we were assessing the size of that set on model before, you can actually get better results. You go down, your loss go down faster. And there is another interesting thing in this paper, which is also something we saw a little bit earlier on the pruning, which is that in these transformer models, the embeddings and the layers, they behave really differently. Okay. So for instance, when you prune, you should prune differently embeddings and layers. And here they show also that it's actually the capacity of the model is really defined by the layers, and all the power law they observed, they work well if you remove the embeddings, okay? If you don't take into account the embeddings when you compute the size of the model. Okay, now there is a last very interesting thing, is that they have two laws for the decreasing loss, okay? One of the laws to decrease the loss is related to the capacity of the model, when you increase the capacity of the model, and one is related to increasing the dataset. Okay. Both can be related together in terms of computation. Like more data means more computation, bigger model also means more computation. So you can collect these two power laws, and what you see on this graph is that you have actually two slopes, which mean that at some point they join together, and you can't really know. You don't really know which loss you should have. Okay, you have one loss which is actually defined by using the optimal data capacity, the optimal data set, and one law is defined by using the optimal model capacity. And at some point, their prediction doesn't fit together, which is actually far above what we've been experimenting right now. It's around the beta parameters regime. And here what they say is that actually the architecture, the transformer architecture, is breaking down. That's what their opinion is. Okay, so all this exploration of more data and bigger models are actually related to one idea. The idea is that maybe there will be a qualitative jump in behavior if we get enough data. Okay, the idea is like maybe just getting more data is enough to see a qualitative, like a phase transition in how the model behave. And there is some hints of this. It's a quite interesting idea, I think. It's very controversial somehow because more data, as I was saying, more data or bigger model, is it really a research program, right? And there's this nice paper from AI2, from Alan Talmor and people at AI2 Israel. They show that actually just comparing BERT and ROBETA, you can notice a phase transition. Okay, so comparing BERT to ROBETA is interesting because they have the same architecture. They are exactly the same models, just that BERT was trained on only 137 billion tokens only, and ROBETA was trained on 2.2 tera tokens. Okay, so ROBETA was really trained on a lot more data. And here you can see this very interesting zero-shot evaluation. So you just take the pre-trained model, you don't fine-tune it, and you ask it questions that are kind of like the Winograd schema challenge question, okay? Here you ask it, a 25-year-old person age is than a 30-year-old person. And the model has to predict if the was younger or older. So it has to actually compare numbers together and use some common sense if you want. And you can see that BERT is pretty bad. BERT is the blue curve. And ROBETA, which is the green curve, is actually like super good at comparing this number in the range of ages for people. You can see the same on size comparison. If you ask ROBETA to compare the size of like the sun to a house, the table to a house, things like that, ROBETA is usually pretty good out of the box. So it has some form of what we would call common sense, and this is out of the box, okay, just by pre-training. It's also even able to compare birth rate, like birth year, sorry. Like if you ask if somebody was born in this year or this year, who is older, so which means it's the reverse than the age, okay? The year, the higher your birth, your year of birth was, the younger you are. And the model is able to do this swap. So that's very actually surprising, I think. Now, there is this big question when you do now fine-tuning, okay? So we've seen that pre-training, bigger data is just better, and actually you may even see some phase transition. Now what about fine-tuning, okay? So fine-tuning means you've taken this pre-trained model on their dataset, and now you want to adapt them on one task, okay? This paper is a very important one from DeepMind. The learning and evaluating general linguistic intelligence. It's a paper that kind of pose a lot of questions. It's an opinion paper, and you should definitely read it, I think, if you want. It's one of the most important of last year's paper. It's like now 1 year old. And what they say is that the recent data set, they're actually too easy to solve with little generalization. Why? Because we have this training data set for the model that are usually often quite big, like MNLI or SNLI or SQUAD. They're really kind of big data set to fine-tune on. And they give models that actually don't really have a good sample efficiency. So let's focus, what does this mean? Let's say we have two models. We have model A. Model A has a 90% accuracy with like 100 training example. But then it doesn't get any better with more training example, okay? It kind of plateau at 90%. Model B takes like 1 million examples to get to 90% accuracy. But then it can increase a little bit and it ends up plateauing at 92%. So if we just do like we do usually, like we compare the model at the end of the fine-tuning, we would say, oh, model B is a lot better because it can reach 92% accuracy. But actually, we should really reward model A, because model A is able to reach a very good score with just 100 training examples. That's really great. That's what we wanted from transfer learning. Okay, that was one of the initial goals of transfer learning, was to make this model work on very small data sets. And this is called sample efficiency. It means how better your model gets with one additional example. There are a lot of other problems with these models which are related. One model is that when you fine-tune on these big data sets, usually we get models that work well really exactly on the training, on the fine-tuning domain. So you have models that work well on SQUAD, for instance, that means they work well on Wikipedia question answering in this very narrow field of question answering. But what we would like, for instance, we don't really want SQUAD models. We would like to have question answering models that would work on any question answering task. And this is related to sample efficiency, because it means that if you just give a few general question answering example, you would like your model to work already well on them. Okay, you would like the model not to need to fine-tune on full Wikipedia to just know question answering Wikipedia. There is a related metrics which is called online code length, which say that how much better your model will get with each additional sample. Okay, it's information theory metric, which actually is related to how much you can compress your model. So it's a very important metrics, and it's actually probably the way to go forward. So here, just a few examples. Here you see if a model was actually trained from. So you can see here the benefits of transfer learning first. So here on the bottom, you see a bird that's trained from scratch on question answering. So this bird is not initialized, is randomly initialized, okay? So it's pretty bad at the end. You just train on the full squared data set and you just don't get very high. Now you can see that if BERT is pre-trained already on, like its usual pre-training, which is the Toronto Big Corpus on Wikipedia, it goes up a lot faster, okay? So this is the benefits of transfer learning, and it reaches nice accuracy. And now if you look at the last part, which is actually a BERT that was pre-trained on another question answering dataset, you can see that it already starts very high. So it means that this model is actually very sample efficient because it was already fine-tuned on another question answering task before. Okay. So this model, when you look at them on online metrics, on online code length metric, you can see that they're actually very different. Because when you actually fine-tune this model, you have to understand the BERT model was pre-trained. Now to fine-tune it, we'll add a linear layer on top. Okay. And this linear layer is randomly initialized. So there is no shortcut here. You will have to train this linear layer. Okay, you cannot really bypass this when you use this model with this task-specific layer added on top. You need to train this task-specific layer, which means that you can't really have zero shot. Okay, and this model we always have to catch up somehow. They always need a few examples to be able to train this last layer, whatever small the layer is. This is what we call task-specific components, and that's a very strong limit to how we can do a very sample efficient model. Okay, now this was just to show you when you actually investigate sample efficiency, you can see that it's also a good way to see if the model is actually learning the task using the knowledge it had from before, or if it's actually learning the task from scratch. So here you see comparison between BERT and ROBETA, right? You know that ROBETA, we've been showing this blue and green diagram. ROBETA has some kind of good common sense, better than BERT, okay? And we can see that because when we fine-tune ROBETA, it's a lot more sample efficient. With just a few examples, it's already catching up. It's already getting better metrics than BERT. And by comparing the sample efficiency curve, which is the performance of your model while you just use progressively more sample to fine-tune it, just by comparing the curve for BERT and ROBETA, you can see, actually you can have a good idea of how much your pre-training was helping to get good performance on your target task. Okay, so this paper is also a very nice investigation of that. And that's actually posed the nice question of how much data should we need? And this actually leads us to the next topic, which is in-domain versus out-of-domain. What we would like, in general, is out-of-domain generalization. What we have, usually, is in-domain generalization. What does it mean? Let's have a look. We've trained our model on question answering datasets. Now we're experimenting with like real life, where question answering is different, like the domain is different, the language people use is not Wikipedia language. And we see there is a strong performance drop, because our model is not really capable of out-of-domain generalization. Here is another nice example on this paper by Thomas McCoy, and which show that actually if you train BERT and it has good performances on like your fine-tuning dataset, like GLUE, okay, you can then test it on another dataset which is out of domain. So how they did out of domain is by having some heuristics. So for instance, you try to make like, for instance, lexical overlap heuristics. So in MNLI, you have two examples, you have two sentences, and you have to say if one entail the other or contradict the other, okay? There are very simple heuristics for that in the dataset, which mean that usually if there is a not, means contradiction. If there is a lot of lexical overlap, it means the entailment. So they build an adversarial dataset called the Hans, which is in the Transformers library. Actually, you can use it. We have an example in it, and which is adversarial. So when there is a lot in this dataset in Hans, when there is a lot of lexical overlap, it's contradiction. The good label is contradiction. Here is an example here. And what they show that is that they can train several BERT on this, fine-tune it with different random seed, okay? So the difference is very small. The difference between this model is very small. It's just the weight initialization of the last layer. And this model, they behave similarly on MNLI. They have like very similar performances. But when you test them on the adversarial Hans dataset, they behave really differently. Okay, they have this huge variability. Some of them are pretty good. Well, none of them is really, really great, but some of them are not so bad, and some of them are really bad. And this means that actually what you see in domain, the test performances you see, just give you no indication of how your model will behave in the real world, which is kind of bad, okay? Here's more example on what they do on MNLI. There are various heuristics they use to design, and you can see you have more or less variability in the fine-tuned model. Some heuristics leads to like really a huge variance, which means that you can't really know how your model will behave in the real world unless you were able to test it on real world data. And some are like have a smaller effect, okay? Now, it's really hard to investigate out-of-domain generalization. So one way is to do this kind of heuristics. Another way is try to build our datasets ourselves so we can control them. So the only really interesting field I've seen this work is the work on compositionality. Compositionality is to investigate how your model is actually able to combine the various parts of a sentence to build a meaning representation. This is very important because we think that in linguistics, compositionality is something important that we do. When I say the blue dog is going out, you kind of gather blue and dog together in a single meaning, and then you combine this with the rest of the sentence to build up the meaning. So there's nice work called SCAN and PCFG sets, which was actually a really long but super interesting paper by Dufke Upkes from Amsterdam University. And they kind of build a huge data set that replicate some natural language data sets. So they build this data set in which you have to combine instruction together to generate an output. Okay, and you have to combine the instruction compositionally, so you can generate the nice output. So you have like instruction like repeat something, and the something will have to be considered as a single entity, and then the repeat function be applied on it. And they were able to naturalize the data set, so they were able to reproduce the depth and the length of like a translation, a very big translation data set, the VMT challenge, okay? So they have this artificial data set, you generate this instruction yourself, but which really replicates well natural language. And when you have this artificial data set, you can actually do some out-of-domain generalization. So for instance, in a training part, you can remove some instructions, some words the model will never see them, or like some way to combine words, and then you can investigate how the model will learn to do that. And I have like one of the most fascinating experiments I saw last year, which is called overgeneralization. Overgeneralization is like super fascinating. It's a bit like when you're a kid, you're learning language and you make mistakes, but these mistakes are like smart mistakes, okay? For instance, you will add ed at the end of a past verb, a verb in the past tense, but it's like an irregular verb. We say, instead of saying I went, you will say I goed, okay? And this is called smart mistake because it means you've learned the rule, you've just not learned yet the exception. And we really want our model to learn rules so they can generalize outside of the training domain, okay? So you can investigate that by putting some irregular verbs in this artificial data set. So here you can investigate that. And the nice thing about this paper is that they compared various architecture. They compared LSTM, they compared ConvNet, they compared Transformer together. And what they see is the really varying performances. Like LSTM, they kind of struggle with this question of overgeneralization. And Transformer are really a lot better usually, and ConvNet are somewhere in the middle. So this is this nice graph where you see on the top you have like a very few examples, like a very few exceptions. So it's kind of hard for the model to learn that. So here you see during the training, the red means that the model is overgeneralizing, the blue means that the model has learned the exception, and the gray means that the model actually don't really know what to do. So it's predicting like random outputs, which is neither the rule, neither the exception. And when you have only a very few sample, like very few exceptions, the model just can't really get them. ConvNet managed a little bit to do that, but Transformer and LSTM, they don't. When you have a lot of exceptions, the model learns just to memorize them. That's what we see in your network, okay? They are very good at memorizing, brute force memorization. And when you're in the middle, you see a bit something that's similar to the way humans learn, which is that you start to have overgeneralization during the training, you have a peak when you actually overgeneralize everywhere, and then you learn that there are some exceptions. So it's very interesting, and it shows that this model are capable of some out-of-domain generalization somehow. Now, talking about in-domain and out-of-domain generalization pose the question of how do you measure the distance between your two domains? And that's a very open question. There is a large body of work on domain adaptation that has tried to show that you can actually extract some feature from your dataset and you can compute some similarity metrics on them. But it's definitely a very open question. How can you measure the distance, like in a statistical meaning, how you can measure the distance between two datasets, okay? And how you can know when you're not in domain anymore. Okay, so talking about in-domain versus out-of-domain generalization, we've talking about this question of sample efficiency, and we saw that using this task-specific component was actually a problem, okay? Because we have to fine-tune them. On each task, we have to fine-tune them, and they are like limiting how efficient we can do. Like, they are like increasing the number of samples we need to learn the target task that we have at the end. And this is actually related to the rise of NLG. So let me show you a little bit, okay? Recently, we've seen more and more text-to-text model. This was started by this nice Salesforce paper by Brian McCain. which was called the natural language decathlon. It was a task, it was a benchmark where you have like 10 tasks, the decathlon, and you have to they were all cast in the same format, in the same framework. They were all cast as question answering task. So if you have translation, you would have a question which is translate this from English to German, and then you have a context which is the English sentence, okay? When you have summarization, we'll actually formulate that as a textual input, which is summarize this, and then you have the news example. And your model has to generate the output. It has to generate the translation, the German translation. It has to generate the summarization. So it's not classification task like we saw before, but it's generation task. GPT-2 is a big model that makes a lot of PR, but was also a very, very nice paper called Multitask Language Model are Unsupervised Multitask Learners. And there was a lot of zero-shot experiment in this. How do you do zero-shot with GPT-2? You do the same. You actually formulate your task with a prompt, which is, for instance, summarize, or for summarization, they did what they called TLDR, too long, didn't read, and then they put the sentence to summarize, and the model is actually trained to generate, it's not trained, it's just zero shot. The model tried to generate some plausible completion, and the plausible completion will be a summary. And GPT-2 is quite good at that. A lot of tasks can be formulated like that, like the Lambda dataset, which is a very interesting task where you try to predict the last word, and the last word of sentence is something that is not explicitly said in the beginning, but you see just implied. For instance, people are talking about giving birth, but you don't say it's not explicitly mentioned in the paragraph. And at the end, you have to complete with the word pregnancy. Okay, so the model has to understand the underlying meaning of the sentence to be able to put in the right word. So this is a completion task. It can be formulated as text generation, where you generate the next word. And we've seen a rise of models like this, which are trained to generate word, and where we actually recast our usual classification or our usual NLP task as text-to-text generation task. Okay? And we've seen that in a lot of recent models. Facebook BART model was pre-trained with a text-to-text objective. So it was pre-trained by giving it corrupt text, where you have like randomly dropped tokens, randomly dropped words, or the text is shuffled. You can see all the objectives here. And the model is trained to regenerate the clean text from that. Okay, so you can formulate this denoising objective as a text-to-text generation, as a corrupt text to clean text generation. And they even train a multilingual model called MBART on this. So we have this both model now on Transformers, so you can try them. And these models, they are trained in this framework. And the most famous one is the recent T5 Google. It's mostly famous because for some time, a short amount of time, it was the biggest model. It was the 11 billion parameter model. And T5 is pre-trained and fine-tuned like this. It's pre-trained with a denoising objective, like the one we saw for BART. And it's fine-tuned in a text-to-text format. So, for instance, on glue task, like MNLI, you have to predict entailment or contradiction. And you will formulate your task as a text input, and model will have to generate entailment, the word entailment, or the word contradiction. Why is this great? This is great because with this, we don't really have to fine-tune any additional layer, okay? We don't actually add any layer to our model. We take the same architecture for pre-training and for fine-tuning. There is nothing to fine-tune or to train from scratch, which means that in theory, we can do zero shot, because no weights needs to be fine-tuned on the target task, okay? The model is ready to be used on the target task. Now, usually this means we need to do like target task informed pre-training. Like we need during the pre-training, that's what is very interesting in the T5 paper that you can read as well. During the pre-training, during pre-training, they prepare the model for this task by giving some example of the fine-tuning as well. So the model knows that it will be asked to do some entailment or contradiction question. But then you can have zero-shot thing. And actually, when you look at what Sam Bauman is saying about glue and superglue is their successor to this task, he said that it's actually really hard now to find some data sets where actually we can have a good classification, like a good NLU task, where you actually can prevent this model to reach human performances, where this model don't even already reach human performances. And usually they reach human performances because they are taking advantage of this fine-tuning task, okay? So in general, I think we should really focus on zero-shot adaptation for transfer learning, like zero shot or very few sample efficiency, zero adaptation. Okay, I hope that's the takeaway of all this discussion. Now let's go back a little bit. We've talked a lot about the quantity of data. We've talked a lot about the size of the models. But all these models, they have some common problems behind this quantity of data, which is their lack of robustness. There are a few things, but for instance, one is like the lack of robustness when fine-tuning. So let's start by talking about that, and then we talk about the lack of robustness with regard to common sense. When we fine-tune these models, you can usually see some pattern like this. So this is a nice graph from Jason Fang's paper called Sentence Occurrence Tilt, and they fine-tune BERT with just varying the random seed. And they show that these models, they are very easily fall into what we call local minima. So you can see this on-off behavior. Sometimes the model works, and with some random seed, it just doesn't work at all. So there was a follow-up recently by UW, Jess Dodge paper, on also exploring when you just vary the random seed for fine-tuning, how the performances of this model are behaving, and they saw the same thing, that the models are very sensitive to the random seed, and they very easily fall into local minima. What I call local minima is that it has bad performances and it's stuck in this regime. Okay. So how we solve that? Usually we solve that with the very brute force approach that you can see for Roberta, for instance, which is that you will train hundreds of models. You will fine-tune hundreds of models on various fine-tuning setup. You're exploring the full hyperparameter space and just keep the best one. Okay, we talk a little bit about that better. Now that's one way to mitigate that. The other way is that we probably need just better regularization. Okay, so the mix-out paper is very interesting. They show that actually when we use dropout, we usually use dropout to fine-tune this model. In dropout, we replace some weights by 0. Okay, but when you do fine-tuning, is it good to actually have the model regularized towards 0? Maybe instead of replacing the weights with 0, we should replace them with the pre-trained value. So we keep the model close to our pre-trained model. Okay, and they show that it's some form of adaptive L2 actually. And the model are behaving better with this regularization objective that you can see on the gray map here. Now they can be a lot more complex regularization, and all the work of Microsoft on the MTDNN models that were topping the glue leaderboard for some time is also all these various regularization you can do. So you can do also regularization where you try to limit the variation in the weights during fine-tuning. There are a lot of ways you can do that to regularize this model, but it's probably the way we should go. And then the last way you can do is actually just to fine-tune a lot of this model and to assemble them. So you can fine-tune them with multitask as well, in which you actually try to increase the domain, the dataset size by gathering several tasks together, and then you train several models that you assemble. And if it's too big at the end, because you have several models, you can just distill them back in a single model, okay? Which is nice, but that's very complex. And actually, when you look at the typical setup right now to get the SOTA on glue that Kevin Clark sent me the other day, it's pretty crazy. Look at this. You have to pre-train your model. So here, as we said, just use as much data as you can, as much compute as you can. Then you have to tune the fine-tuning hyperparameter a lot. Okay, you do data augmentation. So you will, for some specific task of glue, you will start by fine-tuning on WNLI, which is the biggest dataset of glue. So you get some data augmentation. You increase that with unlabeled data, like we saw for the Winograd schema challenge. You increase that with additional labeled data wherever you can use it. Okay. Then you can use some tricks that are actually normally forbidden, but everybody uses to do a pairwise re-ranking where you actually exchange information between examples in the QNLI and WNLI datasets. And then you fine-tune as many models as you can. You take the 5 to the 10 best of all these models, you ensemble them, and you submit that as your results. So this is just crazy compute, and it's definitely overfitting a lot to glue, and it's a big problem. Why is it? Because all these hyperparameter search, now we know that actually if you take any kind of model that was shown by the Gabor Melis paper for LSTM last year, if you fine-tune it well enough, you can actually reach some very good performances. but you've used a huge compute budget to fine-tune it, okay? So this was actually formalized in this nice paper by Jess Judge, which is called Show Your Work, which was an ICL paper last year, which say that we should not just report the end evaluation metrics, but we should report what happened during our hyperparameter search, because it gives information on how much compute you need to actually get this model to good performances. Okay, we talk about that for data sets. We said that if your model needs like a 1 million sample data set to get to good performances, it should be advocated, and we should know that, so we can select also the more efficient model. And you have the same for hyperparameter search. If your model needs a crazy hyperparameter search to reach good performances, we should know about that. So the Show Your Work paper say that you should give these curves that show during all your hyperparameter search how your model was behaving and what was the best one. We see the same thing with standard splits. This data set are splits in standard train and test, which is nice to compare the model, but it leads people to overfit on some standard splits, okay? So the specific heuristics that will work on the standard train split, we can overfit them and almost encode them in the models, which is bad. So this Kyle Gorman paper on Steve Bedrick paper at ACL, we need to talk about standard split, is also very interesting read, and they advocate for random splits. I don't know if random split is the solution. Maybe the solution would be to have several standard splits, but definitely just a single standard split is bad and people overfit. And we can see that because when you try to train this model on other splits, they actually can behave bad. They can be kind of worse than what was expected. Okay, so this was about hyperparameter search, okay? But now there is an underlying question also as well on how our models are behaving. We know that they are brittle and spurious. So let's just see a little bit what this means. Brittles mean that if we change a little bit the input, we kind of see weird behavior. Like this was very visible on the Jia and Yang paper on squad. They show that if you add like a random sentence at the end of a squad context, like the answer that the model predict for the question are totally different. The model is just lost because with this very small modification, we've left the training domain, okay? But our models are also spurious. Spurious mean that they will really do the least amount of work to get the best performances. So if there are easy heuristics that they can leverage, for instance, like we've talked about lexical overlap, when you have a lot of overlap on the two sentences of MNLI, like the model will very quickly learn that a lot of overlap means that the right classification should be entailment. But this is not what we would like. We would like our model to go to the semantic meaning of the sentence and not just to stay on the surface form, just to stay on the lexical overlap heuristics. So this is called spurious. And it's also mean our model are very fragile because in both these cases, when we leave a little bit the training data set, the model gives wrong prediction and fail in unexpected ways. So how can we solve that? There are various ways. Well, one way would be first to get better ideas of how they behave. And I think here linguistics is very important. There's this nice talk by Eli Pavlik, why we should care about linguistics. Well, I think it's really the time for linguistics to come back to NLP and to replace some of the machine learning approach and to help design better evaluation, okay? Because we know that these linguistics rules, they're kind of the underlying rules we would like our models to learn. So they are probably good, not to try to build training data set, but they are probably very good to build evaluation data set and failure evaluation data set. Okay? Now, what we really want to do is to try to provide good inductive biases, which means that our models will want to learn these rules. It will be easier for our model to learn these rules than to learn these heuristics, which is called an inductive biases. That means the model goes toward the solution that we want faster than toward the solution that we don't want. So one idea is all the work on compositionality that we show. We know that compositionality is important for the model to get the good understanding of the meaning of a sentence. So if we can build models that are good on compositionality, that would be one way to incorporate some linguistics. So this is one possibility. So how can we do that? Well, we can trick the architecture of the model. These models, they have these attention heads. So we can try to encode in these attention heads some of this graph that we see in linguistics, like dependency graph, or like shallow, like SRL relation. And this was the nice work, for instance, from Emma Struble, the LISA, the Linguistically Informed Self-Attention for Semantic World Labeling. That was the best paper at MNLP 2 years ago, I think. And where some of the attention heads were actually trained with additionally augmented data with semantic world labeling. Okay, and the model reached better performances because it was able to incorporate these inductive biases. There is a lot of nice work as well on graph convolutional network. For instance, this work by Diego, Andios Basting, and Ivan Titov, where they explored semantics in translation with graph neural network encoding the dependency trees. Okay, so you can try to force the architecture. Another different way is to try to add this inductive bias in the training data. Here is one funny example. It's an anonymous paper on an open review. I think it's very nice. Where they try to help BERT by providing, after the training sample for BERT, like a form of semantic role labeling. So they will say, okay, this word is like a predicate. This word is the first argument, okay? They add this semantic role labeling information after the training. So this forms like just the input for the model. And then at test time, you just don't use this. You just don't input the augmented data. And you see that the model actually gets improved robustness by being trained with this information, okay? They experimented on an adversarial SWAG dataset. Okay, so now probably what we want to do for that is that we probably want to work on pre-training to get some deeper linguistic information in our pre-training dataset as well. Like, for instance, we can add more like linguistically informed span level representation. We can try to have like more modular way to pre-train our models. And this is all very open, but how can we incorporate this linguistic information in pre-training will be probably important as well. An alternative way to make this model robust is to add common sense, because usually they are lacking some linguistic stuff, but as well as common sense. There are some limits. So why do we need common sense? Because we can't learn everything from text. Let's have a look. You know that, for instance, sheep are white, okay? But in text, usually we don't say that because it's too obvious. And on the contrary, we often talk about black sheep because, because that's a common expression, okay? So when you ask a model that was trained on text only, when you ask it, what color is a sheep? It will say, oh, I'm not sure, it's probably black, okay? Because it has no way to know that white is the real answer, okay? This is called the reporting bias. It means that in text, we usually don't state the obvious. We don't write common sense. So how can we help the model learn that? Well, there are various ways. We can try to add like a knowledge base. In the knowledge base, we like have this sheep node and we connect it with color white node. So the model can learn that this is the color of a normal sheep. We can add multimodal. When you show a picture to the model with a white sheep, and the model can just look at it and say, oh yeah, okay, it's white, I can see it on the picture. And then the last part is maybe you can just tell the model. We can have like human in the loop training, like humans are actually learning. The model can ask, what color is the sheep? And then the human or somebody say, yeah, it's white, and then the model knows it. So this is human in the loop training. These are all the way, but you can see that all of them involve something other than text. We need something like more structured, like a database, or we need like picture, we need another modality for the model to be able to learn common sense. So Yejin Choi has been working a lot of common sense. She has done really, really great stuff. The first question is, what is common sense? What is common sense? It's this basic level of practical knowledge in everyday situation. There is a very blurry frontier with bias, okay? Because some part of this common sense is exactly bias that we don't want in our model. But some part is just normal thing. Like here, it's okay to keep the closet door open, but it's not okay to keep the fridge door open because the food doesn't want to go warm, okay? So the way they did that, the way they tackled that is to build a lot of data sets. They build a lot of data sets that try to gather some common sense, and I really want to highlight some of them. Vinogrande is really a fascinating one. It's an extension. Now the Winograd schema challenge is solved. Okay, we've started with that later on, earlier, and now they build a successor to it, which is Vinogrande. They have all this common sense, Cosmos QA, a lot of visual common sense data set. They're all very interesting. And let me just show you, maybe if you want to read just 3 papers, you should read probably Atomic, Comet, and the Vinogrande paper. Atomic is this relation database that I was talking about, okay, that encode common sense, and they crowdsource this. Comet is a nice paper by Antoine Bossuet. It's about using transformers, pre-trained transformers to actually augment this knowledge graph. And Vinogrande is the successor to Vinograd schema. So let me show you just a little bit about Vinogrande, okay? Because that's interesting. We are building all these data sets from crowdsourced information, and actually it's very hard to build nice crowdsourcing setup. And I think they have a lot of experience on this topic, which is very interesting. So here, Vinogrande, the main problem is that we don't want people, first we want people to have ideas and not to generate from just the simplest ideas they have. So they use some way to enhance the creativity with what they call random anchor words. So the people in the crowdsource, the Turkers, they will have this random word that they are supposed to use in their example, the example they are writing. And this helps a lot to make them like creatively create new examples. And they also use like a very strong data validation setup where they fine-tune state-of-the-art models on the data, and they try to remove the data that's too easy to predict. Okay, so this could be like an online data creation process where each time you have a better state-of-the-art model, you actually prune new examples, okay, to remove them. And they show that the state-of-the-art model from now, they have like very bad performances on this, well, pretty bad, and you would need actually a lot of samples to get to human performances. So that's probably the way forward in creating crowdsourced datasets, like trying to make more diversity and try to filter this dataset better. Okay, and this leads us to the same idea for models. Okay, the datasets should now be evolving. They should be dynamically updated as new models come in, and the models have actually the same problem, which is called the continual learning question. What is it? So that's the end of the discussion. It means that BERT was trained on like 2018 data. It will always think that the president of like the United States was the 2018 president, okay? But maybe this will change in the future. Maybe the president, maybe the countries will change, and the model will just never learn this, okay? And how do we overcome that? Well, we need models that are able to evolve over time, okay? But then there is the main problem with this approach. There are a lot of people have been working on continual learning. The main problem is called catastrophic forgetting, which means that you want to learn new stuff without forgetting everything that you've learned before. And here you have different approaches to try to tackle this, from memory to regularization to dynamically growing models. And this is probably the way like NLP should go forward, to have these models that are able to adapt and that are able to generalize to other domains as well. Okay, so that's the end for today. That was a very long talk. I hope you really liked that. And the plan for our NLP series is to do like a lot smaller talk in the future with like more basic information. So if you like this, you can say it and you can send us feedback, and we continue with an NLP series as well.